Hello, I welcome you all for this fourth lecture on the gas turbine power plant. We are discussing the various methods which are used for improving the efficiency of gas turbine power plant. So far, the two different methods that we have discussed in the earlier lectures, that is the intercooling, that was the first arrangement we discussed. The another arrangement that was of interest was nothing but the regenerative arrangement. That was nothing but the reheating arrangement. I'm sorry, we have seen the reheating arrangement for the gas turbine cycle rather. The third arrangement that we are going to discuss in this lecture, so that is known as the regenerative gas turbine cycle. Okay, this is the third arrangement. We are aware with the fact that the exhaust gases which are leaving from the turbine after utilizing their energy, after developing the work in the turbine, the gases which are left to the surrounding, to the atmosphere, the interesting fact is that these gases possess a large quantity of the heat. They are at high temperature, isn't it? The gases which are leaving the turbine, so they carry a large quantity of the heat with them. It is due to the fact that their temperature is quite above, it is far above the ambient temperature. So the energy of these gases should be utilized, it should be recovered so that it will be possible for us to improve the efficiency of the cycle. So let us see how this can be done with the regenerative gas turbine cycle. The gases which are say leaving the turbine and before they are exhausted to the surrounding, so they can be used to heat the air which is coming from the compressor, isn't it? After compressing the air and before it is getting admitted into the combustion chamber, so it is definitely possible for us that the heat of exhaust gases that can be utilized, it can be recovered, and the same heat can be utilized to increase the temperature of the gases after compression. Now the arrangement for the regenerative gas turbine cycle, so this will not say affect the work for the compression. It will not also affect the work which can be obtained from the turbine, but it will definitely help us for reducing the fuel or the mass of the fuel that is required in the combustion chamber, isn't it? So that way this cycle will help us to improve the efficiency of the gas turbine cycle, simple gas turbine cycle. We can see the layout for the regenerative gas turbine cycle. As usual, we have the C, that is nothing but the compressor, okay, air compressor. Then we are having a CC, so that is nothing but the combustion chamber, and at the other end we are having the T, that is nothing but the turbine. Okay, so as usual, the compressor and turbine, they are mounted on the single shaft, and the generator that is mounted at the other end of this arrangement. We can see here that the process 1 2, that is the compression as it is fine. Then the process 3 4 is the expansion of the gases in the turbine, and at condition 4 the gases are leaving the turbine, isn't it? In the normal cycle, it means that without using the regenerative arrangement, the gases at temperature T4 at state point 4, they are exhausted to the surrounding, isn't it? And as we mentioned that they possesses a tremendous quantity of the heat and they are at very high temperature, so we are installing a regenerator, isn't it? So whatever this dotted arrangement that we can see, so this is known as a regenerator. So this regenerator is basically nothing but a counterflow heat exchanger, isn't it? It is nothing but the a two channel counterflow heat exchanger. In one of the channel, the 2 to 2 dash that we can see, okay, 2 to 2 dash, so that shows the flow of the air when it occurs through the regenerator or when it is circulated through one of the channel of the regenerator, and through the another channel we can see that 4 to 4 dash, so that is nothing but the hot gases which are circulated, isn't it? So it means that the heat exchange takes place between the hot gases which are circulated during the process 4 4 dash, and that heat is utilized to increase the temperature of the air passing through the another channel of the regenerator, so that is nothing but the process 2 to 2 dash. Okay, so in the absence of the regenerator, the temperature of the gases that is entering the combustion chamber would have been the temperature T2, but as we are heating this air before admitted to the combustion chamber, so we get the temperature T2 dash. Okay, so definitely the T2 dash will be higher as compared to that of the T2. Okay, so this is what the arrangement which can be utilized for a regenerative gas turbine cycle. Okay, so 1 2, that is nothing but the compression process. 2 to 2 dash, so that is nothing but the heating of the air in the regenerator by utilizing the energy of the exhaust gases from the turbine. The process 2 dash 3, so that is nothing but the heat addition in the combustion chamber. 3 to 4, asentropic expansion of the gases in the turbine. And last process, that is 4 dash, so that is nothing but the energy which is recovered by the hot products of the combustion leaving the turbine and before they are exhausted to the surrounding. Now the point to be noted here that we know that the regenerator, we are calling it as a heat exchanger, and in the previous unit for the heat exchangers we have seen that the performance of the heat exchanger is expressed by a term known as the effectiveness, isn't it? So effectiveness is defined as the ratio of actual heat transfer to the maximum possible heat transfer. Okay, so this definition we are quite aware as we have discussed this concept in the previous unit. Now if the effectiveness of this regenerator heat exchanger would have been say 100%, then it is possible for us to increase the temperature of the air from T2 to the T2 dash, that should be equal to a T4, isn't it? The maximum temperature that can be raised for the air, so from T2 to the T2 dash, so that would be equal to the T4, isn't it? And similarly, when the gases are circulated through the regenerator, so they can be cooled from T4 to T4 dash and to the lowest possible temperature equal to T2, isn't it? Okay, so the gases can be heated to the maximum temperature of T2 dash, that is equal to T4, that is air can be heated, and the gases can be cooled from the lowest to the lowest possible temperature of T4 dash, that is equal to temperature T2. Okay, so that is what the regenerator effectiveness or the heat exchanger effectiveness that comes into picture. So this is what the temperature entropy diagram that we can see here for the regenerative cycle. The process 1 to asentropic compression of air in the compressor. 2 to 2 dash, so that is nothing but heating of the air which takes place in the regenerator before admitting to the combustion chamber. 2 dash to 3, the process of isobaric heat addition, constant pressure heat addition in the combustion chamber. In the process 3-4, asentropic expansion of the gases in the turbine. And 4 dash, so that is nothing but the heat which is recovered for the exhaust gases from the turbine before they are left to the surrounding. Okay, so by making an usage for the definition of the regenerator effectiveness, actual heat transfer to the maximum possible heat transfer, epsilon regenerator effectiveness, so that can be given as H2 dash minus H2 divided by H4 minus H2 dash. Okay, so those are nothing but the in terms of the enthalpy. Okay, H2 dash minus H2 divided by H4 minus H2 dash. And the equation for the efficiency for the regenerative cycle, so again the definition that remains the same, we can write down as the net work obtained from the cycle divided by the heat supplied in the cycle, isn't it? So net work is again is nothing but the turbine work minus the compressor work. So the enthalpies are expressed here H3 minus H4. So we know that the 3-4 is nothing but the expansion process. And similarly the H2 minus H1, that is nothing but the compression process. Okay, so H3 minus H4 represent the turbine work, and H2 minus H1 that represent the compression work. H3 minus H2 dash. Okay, H3 minus H2 dash. So 2 dash to 3 is the constant pressure heat addition. So H3 minus H2 dash that represent the heat added to the constant pressure process, isobaric process. Now if this regenerator would have been say absent, then the heat supplied would have been H3 minus H2. Okay, instead of H3 minus H2 dash. In the absence of the regenerator, the heat added would have been H3 minus H2. So this number would have been larger as compared to the H3 minus H2 dash, isn't it? It means that for the same work output, we require the lesser amount of the heat to be supplied. So your numerator may remain as it is, but definitely there will be reduction in the denominator value. So that will help us to increase the thermal efficiency for the regenerative cycle. And if I substitute the values for the temperature, I express the regenerative cycle efficiency in terms of the temperature. So I can express as the Cp into T3 minus T4. So T3 again, it is nothing but the maximum temperature in the cycle at the temperature of the gases entering the turbine. T4 temperature of the gases leaving the turbine. So Cp into T3 minus T4. Okay, Cp into T3 minus T4 is nothing but the turbine work. Okay, so from this we subtract the compressor work. So T2 temperature after compression, T1 is the temperature before compression. So Cp into T2 minus T1, so that is nothing but the compression work. So numerator represent the turbine work minus the compression work, and denominator Cp into T3 minus T2 dash. So T3 is the temperature after the heat addition, and T2 dash is nothing but the temperature after the intercooler. Temperature after the regenerator. It is not the intercooler, it is a regenerator, or it is the temperature before it enters the combustion chamber. So Cp into T3 minus T2 dash. So this term represents the heat which is supplied during the constant pressure process. Okay, so that way the arrangement for the regenerative cycle can enhance the performance of the simple gas turbine cycle. So this was indeed the last arrangement which was used for increasing the thermal efficiency of simple open cycle gas turbine power plant. Okay, so let me summarize the few important points for the three different methods that we have used, that we have discussed. The first method that we discussed was nothing but the intercooling arrangement, and we prefer the intercooling arrangement whenever we are having the multi-stage compression process. Okay, when the pressure ratios are very high. So this multi-staging, by utilizing the intercooler, that helps us to reduce the work of compression, as we are aware that the majority of the power developed work obtained from the cycle that is required for operation of the compressor. Okay, in one of these lecture we have seen that it is 66%, or approximately 2/3 of the work is consumed by the compressor. So that's why the intercooling is beneficial for us to reduce the work of compression. Then we have seen the reheating cycle, where we use the two different turbines, high pressure turbine and low pressure turbine, and we install a reheater in between these two turbines. And the reheating arrangement doesn't affect the work of the compression, isn't it? But it increases the work which is obtained from the turbine. Hence the net work increases, and heat supplied, so that is also increasing. So that will help us for increasing the thermal efficiency. And the last arrangement that we have discussed in this session, in this lecture, was the regenerative gas turbine cycle. Okay, so regenerative gas turbine cycle that help us to reduce the mass of the fuel which is required during the constant pressure heat addition. Okay, so these are the three different methods utilized for improving the performance of the gas turbine cycle. So we'll stop here for this today's lecture. So thank you very much for your kind attention.